number 1. Question number 2, if we have a renormalizable theory, so we have a small number of operators and it's renormalized, the theory after renormalization, the effective theory, does not look renormalizable. It can have higher dimension operators. The point about the special operators which appeared in the Bayer Lagrangian is that all the infinities can be absorbed in them, and the rest, which are calculable, are finite. So this is kind of a clarification. And we saw that in the example of the O'Rafferty model, where we integrated out stuff at the scale m, and we got a low energy effective Lagrangian where the high dimension operators are suppressed by powers of 1 over m. We can still compute loops in the low energy theory. This is not renormalizable, but this theory is cut off at the scale m. This is kind of a general comment. So as I said, the talks have 3 parts. Part 1 was spontaneous supersymmetry breaking. We're working basically at tree level and 1 loop correction. We saw a pseudo-moduli space of vacua, inequivalent vacua parametrized by a scalar field. They were degenerated tree level, but after 1 loop radiative corrections, a potential is generated. This is unlike what you see when the ground state is supersymmetric. When the ground state is supersymmetric, the vacuum degeneracy cannot be lifted in perturbation theory. But here at 1 loop, a potential was generated. In the case of the O'Rafferty model, we ended up with 1 ground state after the radiative corrections have been taken into account. 1 ground state at the origin in which the R symmetry is not spontaneously broken. The spectrum is completely massive in the end of the day, but supersymmetry is spontaneously broken, and therefore there is 1 massless fermion, which is the Goldstino. After that, we discussed a more generic superpotential. So again, we have in mind some theory at a high scale, which gets some non-perturbative effects and so forth. At low energy, we have a theory which has only chiral superfields, which has some complicated superpotential, which is a function of the chiral superfields. And we argued that typically there are stationary points, critical points, in that superpotential, because we have the same number of equations and unknowns. Having a global symmetry doesn't help. And that's basically why it's so hard to break supersymmetry. However, if there is an R symmetry, we argue that we have more equations than unknowns, and then typically supersymmetry is spontaneously broken. There are, however, a few exceptions. For example, the function in the superpotential might not be a generic function. We might land on something which is not generic, and then it's true that we have more equations than unknowns, but the equations are related, and therefore we can find a solution. Also, if the R charges are non-generic, we can find examples with an R symmetry in which supersymmetry is unbroken. For example, imagine we have this theory. Then there is an R symmetry under which phi has R charge 0 and x has R charge 2. And supersymmetry is unbroken because d phi of w equals 2x phi, and dx of w equals phi square minus mu square. So from here, we can set this to 0 by setting phi equals plus or minus mu. And then we come here and we set that to 0 by setting x to 0. So this theory has 2 supersymmetric ground states, even though it has an R symmetry. And if you go through the proof with getting a power out, with and so forth, you will see exactly why these are non-generic R charges. But in most applications, the R charges will be various rational numbers or even irrational numbers, and this peculiarity does not happen. So we conclude that it's not quite a rigorous theorem because we need to assume genericity both in the charges and in the function. Supersymmetry is broken if and only if there is an R symmetry. Now let's imagine we have an R symmetry, but we explicitly break it. So what will happen? 2 things will happen. First of all, we explicitly break the symmetry. The theory does not have the symmetry. And therefore, by the same result, so we have U1R if and only if SUSY is broken. That's kind of a quick summary, a quick guideline to remember. So imagine we have a theory in which the R symmetry is explicitly broken. So we have a superpotential W, which is a sum of 2 terms. This is invariant This is U1R invariant. And then we have a small coefficient epsilon times W1, and that breaks U1R. It's easy to do that, and I'll soon give examples. We can take, say, the O'Rafferty model and add epsilon times something that breaks the R symmetry. Or we can take our example number 1, which had a superpotential linear in X, and we add epsilon X squared, for example. That breaks the R symmetry. So what do we learn? We can learn a few facts. First of all, the full system does not have an R symmetry. Therefore, by this result, SUSY is unbroken. However, for epsilon equals 0, there is an R symmetry, so SUSY is broken. So let's plot the potential. For epsilon equals 0, supersymmetry is broken, and we have one ground state, and we see that supersymmetry is broken because the ground state energy is non-zero. That just follows from the fact that for epsilon equals 0, so this is the potential for epsilon equals 0, and this is V, and this is some generic scalar field. So for epsilon equals 0, we have an R symmetry, and supersymmetry is broken. Now we turn on a small perturbation. What should we do? Well, near this vacuum where everything is finite, we have a nice vacuum. Not much can change. So I have colors here. So now we'll have epsilon non-zero, but much less than 1. So we're going to get something here which is not a big much different than for epsilon equals 0. However, when the fields become large, this thing becomes important, and at fields of order 1 over epsilon, or 1 over positive power of epsilon, very, very far, supersymmetry must be restored, because we know that in the full system, supersymmetry is unbroken. So without doing any calculation, just very, very generally, just writing such a superpotential, at phi, which is very large, of order 1 over epsilon, or 1 over epsilon to some positive power here, we find his supersymmetric ground state where the vacuum energy is exactly 0. So a corollary of this statement is that approximate U1R SUSY breaking. So the ground state here, at epsilon equals 0, it's not supersymmetric. For epsilon small, it continues to be non-supersymmetric. Maybe it moves a little bit, maybe it lifts a little bit, but the shape, it's still a minimum. And somewhere very far, the supersymmetric ground state appears. And if it's very far, it's clear that the tunneling from here to here is suppressed. Typically suppressed by e to the minus 1 over epsilon to a power. And when epsilon goes to 0, this thing becomes absolutely stable. So we end up with a metastable SUSY breaking state. And all we need is an explicitly broken approximate R symmetry. This is extremely important for phenomenology. Because for phenomenology, we have in mind some sector that breaks supersymmetry. And it doesn't matter at the moment whether it breaks it at tree level or non-perturbatively or whatever you. We need something that breaks supersymmetry. And by our argument, it must have an R symmetry. That has constantly been a problem for model building. It's been a problem for model building because this R symmetry leads to a lot of trouble. Number one, we need gluino masses in the end of the day, or gaugino masses in general, Fotino, Wino, Bino, gluinos, etc. All these explicitly break the R symmetry. So we must have some R symmetry breaking. Otherwise, there is no way you can compute diagrams all day. There is a symmetry that prevents gauge-no masses. One might say that maybe there is an R symmetry and it is spontaneously broken. We didn't see that in the orafity model, where the R symmetry is not spontaneously broken, but there could be other examples where there is an R symmetry, it's spontaneously broken, and it eventually leads to gauge-no masses. This can happen. However, if we have an exact global symmetry and it's spontaneously broken, the spectrum has a massless Goldstone boson. Comes under the name of an R axion. And there were all sorts of mechanisms to give it masses. Gravitational effects can help. Sometimes there's an anomaly. But the theory, as you see, even without starting to write down a theory, we see that it starts getting awkward. We need to have an R symmetry. It has to be spontaneously broken. We need a mechanism to lift the axion. A much simpler way out is to say that we have an R symmetry, but it's approximate. It's explicitly broken, and therefore if it's spontaneously broken, the axion gets a mass. If it's not explicitly broken, it doesn't matter. If it's not spontaneously broken, it doesn't matter. We can still get gauge-no masses. But what we learn from all that is that if that's what we need, then it must be, based on this reasoning, that we live in a metastable state. So again, there are a number of assumptions here and some loopholes in this general reasoning. I'll mention them again. The superpotential might be non-generic. The R charges might be non-generic. I mentioned that earlier. There are also gravitational effects, which I neglect here. I assume that the entire model is described only within local quantum field theory without gravity. But making these assumptions, very general considerations of phenomenology, and you don't need to be a phenomenologist to know that we must have gauge-no masses, and we cannot have exactly massless Goldstone bosons. We don't need the LHC for this information. This by itself tells us that we must live in a metastable state. So that's one thing I wanted to mention here. I'd like to show an example to show that, you know, this sounds like I'm kind of pulling a fast one in front of you, because I'm getting a very powerful result with doing practically nothing. You know, what did I do? I wrote W0 plus epsilon W1, and I didn't do a calculation. So let me show an example how these things work. So we're going to start with the same orafity model we had yesterday. So this is our W0, and it has an R symmetry. Just for fun, let's write the R charges. From here, it's clear that X must have R charge 2. From here, since X has R charge 2, phi 1 must have R charge 0. And if phi 1 has R charge 0, phi 2 must have R charge 2. So there's an exact U1R symmetry. Indeed, supersymmetry is spontaneously broken. So let's add to it epsilon. And to make the expression simpler, I'll put an m over 2 here, phi 2 square. This term has R equals 4, because phi 2 has R charge 2, and therefore it explicitly breaks the R symmetry. So without doing any calculation, it's clear that supersymmetry should be restored. Let's compute it. Well, I'll leave it a little bit as an exercise for you. This superpotential has stationary points, and the stationary points are phi 1 and the SUSY vacuum equals plus or minus root minus 2f over h. Phi 2 in the SUSY vacuum is minus plus 1 over epsilon square root of minus 2f over h, and x in the SUSY vacuum equals m over h epsilon. Notice that phi 2 and x, their vevs, are proportional to 1 over epsilon. So as epsilon goes to 0, these supersymmetric ground states are very far. This is to be distinguished from the metastable state. Metastate with SUSY broken, which had x equals 0. In fact, when we include corrections due to epsilon, this shifts a little bit. So this is the ground state we talked about yesterday. And by adding this term, a new ground state appears very far. Now, the radiative corrections that we discussed yesterday really stabilize this ground state. They lead to a potential around it. So this is a nice localized minimum. And the fact that very far there is another ground state, which happens to be lower in energy, has 0 energy. This one has positive energy. It doesn't matter for local physics around here if we don't wait too long. If we wait long enough, this state will decay into the other one. So this is an example of the general reasoning I had here. And I recommend an exercise that you look at this potential, you calculate the spectrum, tree level, you do the one-loop correction, and you see that everything indeed works. And it's kind of guaranteed to work because near the origin, we can neglect this term, and it's the same calculation as yesterday. And far from the origin, once we have a supersymmetric ground state, it remains supersymmetric. The spectrum is supersymmetric, so the potential doesn't change much. So this is an explicit realization that gives a potential which looks like that. Any questions about that?
The general statement you make doesn't apply if you just have two fields, because then, supposing you have two fields, then you can't, in other words, the rapidly needed 3 to get his model.
Because it was renormalizable.
So, yeah, well, yeah, that's right. But so supposing
My example 1 had only one field.
Yeah, but supposing I don't know about normalizability, then if I just write down a potential with 2 fields, I could write down one that has an arc symmetry. So I then expect SUSY breaking. But you say that
Excellent. Do you want an example with one field?
But Arafaday couldn't find it because he was insisting on renormalizing.
Right. But if you look at, let's look at example 2. Yeah. Example 2 had a nice minimum. So let's do an example 2. So this would be 2 prime, because I modified example 2. Example 2 had some k, which was a function of x dagger x, doesn't matter. And w was mu square x. So that has an R symmetry, because x has R charge 2. Let me add here epsilon x squared. And let's say that this was approximately 1 minus, I forget what I put here yesterday. Sorry. Some constant, something like that. That was the example. And let's even put let's make it dimensionally correct, so C is dimensionless. This was example number 2 yesterday. And I'm adding epsilon x squared with some number here, doesn't matter. Okay? So what does the potential look like? For epsilon equals 0, it looks like that. And because the derivative is mu squared, and this term in the Kähler potential curves the potential like that. However, there's a supersymmetric ground state at the stationary point of W, in which x is, let me put a 2 here, is minus, so this is in the SUSY state, x is minus mu squared over epsilon. So the potential does something which depends on k, and somewhere, let me change this sign so it will be positive, at mu squared over epsilon, it hits 0. So this is an example with one field. So it's even better than what you bargained for.
Is it always the case that the potential has to be bounded?
From below?
No, from above, between the two minima.
Well, if the SUSY potential and the Kähler potential are regular functions, and and the second derivative of k doesn't have a zero, then it's bounded. Otherwise, there could be a singularity.
If in your metastable state where we live, we effectively can neglect the asymmetry breaking, what happens to the Gino mass mechanism?
Okay, so the asymmetry, the explicit breaking must be large enough to give Gino masses. And if you just throw in some numbers, it's not a problem. You can make it work. In fact, when people tried to construct realistic models in the mid-90s, they noticed this problem with the asymmetry. They didn't formulate it in this language. In fact, they saw that there was difficulty getting Gino masses, so they added extra terms in the Lagrangian, not noticing that it breaks the asymmetry. And upon further scrutiny, it turned out that all these models have supersymmetric ground states elsewhere in field space. More specifically, there were various messengers. They assumed the messengers don't have a vev. They found some supersymmetry breaking state, but it turns out that somewhere the messengers get a vev and supersymmetry is restored. And this was noticed by these people, and it was assumed that this is some kind of a nuisance. The model was not elaborate enough, and if you only add more fields and more couplings and change something, with enough ingenuity, we can get rid of the supersymmetric state and be left with a stable one. I'm now arguing that this is inevitable. So if you really want these models to work, we must be in a metastable state. So it's not a coincidence that in all these examples it worked like that. I'm telling you that because in all these examples, the Gino mass was large enough.
Isn't there additional feature that the perturbation you're adding is one that's going to change the Witten index?
The Witten index changes because things come in from infinity.
Yeah, but I mean, you could consider adding a perturbation that, for example, was lower order in field, the lower order polynomial, but wouldn't change the Witten index, and then the general statements you're making.
I think it will not. No, I think it will not. I think you will always restore supersymmetry, and the argument is basically this pseudo-flat direction. So if you work classically in all these models, so if you have a canonical Kähler potential, which is important for your argument with the power counting, if the Kähler potential is not canonical, then everything goes. But with the canonical Kähler potential, you can prove that whenever supersymmetry is spontaneously broken, there is this pseudo-flat direction. And along this direction, every perturbation is important. So this is where vacua are coming from infinity.
It's crucial that the argument here that W1 dominates at large field values.
Well, there are different fields. There are different fields. I'm telling you that there is always a direction in field space in which W1 will dominate. Because W0 always has at least one direction in field space where it's exactly flat, classically.
So
that's why it's sensitive.
Then there's a kind of generic, so a non-generic W1, which.
That's correct. A non-generic that's exactly right. A non-generic W1 will lead to supersymmetry breaking without an asymmetry. Conversely, you can have so if W is non-generic, everything I said doesn't apply, because in all these counting of equations and unknowns, I assume genericity. But if you look at specific examples that people studied, all these statements about genericity just apply. The R charges are 7/5, and W is, and we'll have that maybe not today, but in the next lecture. We'll have very complicated functions for the superpotential, which are generic. So this ends part one of my talks. But it leaves something to be desired because we can break supersymmetry. We've learned how to do that. But the scale of supersymmetry breaking is put in by hand. We would really like the scale of supersymmetry breaking to arise dynamically. The idea is that there's a small coupling constant, say G, which is small but not very, very small. Small, let's say, at the Planck scale. And then a non-perturbative effect, like e to the minus 1 over g squared, is a very small number, and that's responsible for the big hierarchy. So the idea is that supersymmetry will be dynamically broken by dynamical mechanism. such that at low energies it's described by one of these models that we discussed. But the coefficients in these models are exponentially small because of some dynamical effect. But in order to study these models, I still need to have a digression about non-perturbative effects in supersymmetric gauge theories. So this leads me to part 2 of these talks, where we discuss supersymmetric gauge theories and their non-perturbative effects. So you were subjected to quite a lot of that last week, and I apologize for subjecting you to more of that this week. Brian Wecht gave some talks, and I looked at his notes. They looked pretty good to me. I'm sure he did a wonderful job. But I decided to present this subject in a self-contained way, so even if you missed Brian's talks, you can still learn it here. But even if you heard Brian's talks, I will do it from a different point of view than the one he took, where I'll emphasize different points, although there will be some overlap. So the title of this section is SUSY QCD. We'll focus on a particular gauge theory, which is very much like ordinary QCD, except that it is supersymmetric. It's an SUN gauge theory. Now denote NC by the number of colors. And we have NF flavors. Q in the fundamental and Q twiddle in the unfundamental. So that's the gauge theory. And an important thing to remember, which for some reason young people these days don't remember, is that when you want to analyze a quantum field theory, the first thing to study is the classical theory. There's a lot of physics to extract from the classical theory before we jump to quantum mechanics. And I really don't understand why the young people don't appreciate that. So there's an important fact about these classical theories is that their potentials have flat directions. So the potential, V, classical potential, is a sum over gauge generators. Let me not worry about factors of gauge coupling. What is called this D term squared. A runs over the generators of the gauge group. And the expression for D is a trace Q TA. I'll define in a second everything. Q dagger minus Q twiddle star TA Q twiddle transpose square sum over A. Where Q and Q twiddle are rectangular matrices, flavor running this way, and color running this way. And the TA are the standard traceless Hermitian matrices, which are the generators of the gauge group. I hope I didn't mess up the flavor and color. Yeah, I didn't mess it up, because the color from here multiplies the T, and here we have a dagger, so we transpose and take complex conjugate. So we want to set all these guys to 0 classically. See, this is a sum of positive quantities. The potential is a sum of non-negative quantities. So the vacua are when these can all be set to 0. So we can just solve these equations. And the solution looks differently depending on the number of flavors. So if the number of flavors is less than the number of colors, the most general solution, which set these guys to 0, is up to gauge symmetries and global symmetries is of the form V1, V2, VNF. Notice it's smaller than the number of colors, and we have zeros here for the rectangular matrices. And you can plug it in here and check that it is a solution. So we have a rather large space of inequivalent ground states, classical ground states. The color indices run this way. So the waves here are like Higgs. We have the Higgs mechanism here. The waves here break the gauge symmetry. So SUNC is spontaneously broken to SUNC minus NF, which acts on the last columns here. And we can parameterize these ground states by gauge invariant fields M, which are Q twiddle, Q transpose. Notice that here we don't have any star, no dagger, no star. So Q and Q twiddle are different holomorphic fields. They're both chiral. So M is a chiral superfield, and we have NF cross NF of them, chiral superfields. And I'll leave it as an exercise for you. Check that under the Higgs mechanism, some of the generators here were eaten in the Higgs mechanism. We started with some number of chiral superfields. Some of them were eaten by breaking this to that. And the remaining number of chiral superfields which are not eaten is NF square, and they can be parameterized by such an M. And the word M, the letter M here, is the first for meson, because this is like a quark bilinear, quark antiquark. And we can put the color and flavor indices here. It's actually a general result. It was known in mathematics for more than 100 years that when you solve these D-term equations, the solution can be, you solve the D-term equation and you mod out by the gauge group. The space of solutions can be parameterized by gauge invariant polynomials in the chiral superfields. That's not the way they formulate the theorem, but this is the way we would formulate the theorem. And here, the only gauge invariant polynomials we can form are these M's. So they give us a nice parametrization of what we can call the classical modular space of vacua. And this is simply the space of these matrices M, NF square dimensional. So if we go to a generic point in the low energy along these moduli spaces, the low energy theory includes this gauge theory and NF massless fields, which are NF square massless fields, which are neutral under the gauge symmetry. And they couple to the gauge theory only through high dimension operators. So the extreme low energy theory is just this gauge theory, the unbroken one, plus NF square chiral superfields. Things are a little bit richer when NF is larger. I'll put it here. So if when NF was smaller than NC, see the matrices were fat, there were more colors than flavors. For NF bigger or equal NC, the matrices are square when it's equal and are kind of skinny when it's larger. And the most general solution is V1 to VNC, which is smaller, and 0 here. And Q twiddle is V1 twiddle and C twiddle, 0 here and 0 here, such that VI absolute value square minus VI twiddle absolute value square is independent of I. The fact that here we have more options, that we can have these guys different insofar as their difference between them is independent of I, follows from the fact that the gauge group is SUN rather than UN. So the diagonal generator here, T, which is like the identity, doesn't contribute, so we lose one equation, and therefore we have more freedom. So this is just straightforward algebra. There's no reason to do it in public. But I do want to give the gauge invariant description of these states, of all these moduli space of vacua. So how can we form gauge invariant polynomials out of this? The first gauge invariant polynomial we can form is like M, Q twiddle Q. So these are NF square fields. We can also form baryons that we could not form before. So where the color indices are I1 up to INC with an epsilon on I1 and C, and some flavor indices A1 up to A and C. So this B is an antisymmetric tensor in flavor. This is not something we could do with fewer flavors than colors, because we need to antisymmetrize NC different colors. And if we antisymmetrize NC different colors, we have to antisymmetrize the flavors, but if we don't have enough, as was the case above there, we don't have such a gauge invariant thing. And similarly, we can form a B tilde. At the generic point in these moduli spaces, the gauge group SUNC is completely broken to nothing, because we have enough vevs to completely break the gauge symmetry. So if you try to do the calculation we I recommended before, asking how many chiral superfields there should be, you start with how many there were, you subtract NC square minus 1 that are eaten, and you will see that you are left with some number. And here we have way too many. Just have too many. So what's going on here? What's going on is that this parametrization is redundant. In other words, is overcomplete. In other words, these fields are not independent. For example, the matrix M, which is Q twiddle Q, where Q is such a long matrix. I need a transpose. Where is the transpose? The transpose is here. I apologize. So this is a long matrix like that times the transpose of that. So even though it is an NF by NF matrix, its rank is less than or equal than NC. Is that clear? You just multiply matrices, rectangular matrices, and it has only NC columns, so the rank is. And therefore, it does not have NF squared degrees of freedom. It has fewer degrees of freedom, because the rank is constrained. Similarly, the baryons are constrained. So let's take an example, a very explicit example. Imagine NF equals NC. So we don't have a problem here. The rank of the matrix is OK. But the baryon is like the determinant of the matrix Q. And B tilde is the determinant of the matrix Q tilde. For NF equals NC, these are square matrices. So the baryons are simply the determinant. And therefore, the determinant of M minus BB tilde equals 0. So there is a constraint. It's again property of matrices. So just as here the classical moduli space was the space of M's, in this example, the classical moduli space is the space of all M's and all B's such that M equals BB tilde. And we can try and add flavors, and the constraints become more and more complicated, and I will not do it here. This is all I wanted to say about the classical theory. We can discuss it in more detail, but I will not do it here. What happens to all these vacua? We found whole space of vacua. What happens to them in perturbation theory? Not much. Not much due to the non-renormalization theorem. So we had this classical moduli space of vacua. That remains true to all orders in perturbation theory. So now we can graduate to non-perturbative physics and ask what happens to this theory non-perturbatively. But before I do that, I should pause for some questions. I'd really like to encourage the students to ask questions. I'll make it with a threat. If you don't ask questions, I'll speed up. Please.
So with kind of in general, okay, so this is like a simple case here for the determinant relation. In general, will you have like relations on determinants? Like, what will the general kind of expression for your modular space?
It's getting increasingly more and more complicated as you add flavors. And I don't think there's a general formula for which is known for the relations. And in various examples, well, you can repeat this exercise, say in the n equals 4 theory, for example. And there the answer is actually interesting. And I think some members in the audience know more about that than I do. How to enumerate the independent relations and subtract the relations, and as you keep going, the relations are also not independent, so there are relations among the relations, and this is again a very common thing, and mathematicians understood that hundreds of years ago. So you have some space and there are some relations, but the relations are not independent, so if you count how many independent directions there are in this modular space, it's the total number minus the number of relations, but then you have to add something because the relations are not independent, and that by itself might be overcounting, so you have to subtract, and you keep going until it stops. This example, in fact, the next one up, are very manageable. So I leave it as an exercise for you to do the next one up, and the answer is in the literature. So you can pick. More questions, please.
Does this modular space have a certain geometrical structure for n plus 1?
Yes, it's a Kähler manifold. It's complex, of course. It's scalar, and this space has singularities. For example, when m equals 0, it's singular. You know how you find the singularities. You have to satisfy this equation, and then the tangent vanishes. And that's at these points. And the physics of the singularities is easy to understand. The singularities mean that there are more light degrees of freedom, physically. So physically, whenever there is a singularity in the modular space, the singularity is telling us that we have left out some light degrees of freedom. This is a general rule that is worth remembering.
That's where the gauge theory enhances again, right?
The gauge symmetry is enhanced because we don't break. For example, imagine m has a vanishing eigenvalue. Then this is 0. So imagine b and b tilde are 0, and m has a vanishing eigenvalue. More concretely, it happens when one of these v's and one of these v tildes vanish. Then the gauge group is smaller. Instead of SUNC, the NCUNC is broken to SUNC minus 1, so there are more, or SU2, depending on what you do. I can't think on my feet. But there's an enhanced gauge symmetry, and that's the physics of the singularity. No more questions. Okay, so we move to non-perturbative physics, and the point to start is the theory without flavor. So that should be relatively easy. So this is the pure gauge theory. And it has only the gluons. And it's always a good idea to form gauge invariant objects. So we form a gauge invariant object, which is a closed relative of f mu nu square in ordinary gauge theory. and it's convenient to put minus 1 over 32 pi square. I put the 32 pi square here, and by doing that, I'll save a lot of work. There will not be any more pi squares in the remaining. Times trace W alpha square, using Wesson-Bagger notation. So this is 1 over 32 pi square. It starts with a Gluino bilinear, the first component of that, plus dot, dot, dot. There's a theta square, a half f mu nu square, plus dot, dot, dot. So that has a lot of components, and it is a chiral superfield. So I'm going to state here without a proof, although the proof can be given, that this field S, which is 0 classically, acquires an expectation value in the quantum theory, which I'm going to write in the following form, and I'll explain the notation in a second, 1 over NC. So first of all, lambda. Lambda is the dynamically generated scale in the theory. It's some cutoff scale, e to the minus 8 pi square over 3nc g square at the point of the cutoff, which is much less than m cutoff. This can be seen already at one loop. At one loop, the gauge coupling runs. And as it runs, very high energies, we have a small but not too small numbers. The small but not exponentially small number g cutoff. And the one loop beta function is written here. And the fact there is a minus sign here is thanks to David. Or asymptotic freedom. So at very high energy, the theory is weakly coupled. We have gluons and gluinos, and they weakly interact. But as we move to lower and lower energies, the interactions between them become strong. And at low energies, such an expectation value is generated. And the theory has a gap. There is no massless particle. That's important. All these things can be proven, but I'm not doing it here. I'll use that to derive other results. We can turn the story around, derive some of the results, and then derive this result. I put the coefficient here 1. That's really a definition of big lambda. But the power here is so big that we can actually use known subtraction schemes. So this is a choice of subtraction scheme. We can use known subtraction schemes, and the subtraction scheme that I use here is called dimensional reduction bar, which is the most common subtraction scheme in supersymmetric theories. And with this subtraction scheme, and with my conventions with the 32 pi's and pi square and all that, the coefficient here is exactly 1. So that shows you that in these theories we can calculate. So we know all the numbers of order 1. It's not just an order of magnitude estimate. Finally, the classical theory has an R symmetry under which the gluinos rotate. This R symmetry is anomalous. In the quantum theory, it's explicitly broken by the anomaly to Z2NC. So there's a discrete Z2NC R symmetry. And by this expectation value, this discrete chiral symmetry is spontaneously broken to Z2. That's why I wrote the answer here, and I didn't divide by the NC. So lambda to the 3NC is a well-defined number. We raise that to the power 1 over NC. There are NC different phases here, NC roots of unity, corresponding to the NC different vacua of this theory, which are in the orbit of Z2NC. So again, there is a Z2NC discrete chiral symmetry. There are NC vacua. We act with the symmetry, we move from one to the other. This is the statement that the chiral symmetry is spontaneously broken.
Your previous statement about the relation between R symmetry and breaking of SUSY, did that require a U1
It continues.
continuous
It continues.
symmetry?
That's
That
right.
wouldn't apply.
That's right. That's why this theory doesn't break supersymmetry. So in the old days, the argument was much more complicated based on the Witten index and twisted boundary conditions and the finite box and so forth. Now I will just say there's no continuous R symmetry, so it doesn't break supersymmetry. That's a little bit easier,
A little bit less rigorous.
but works in many examples that the other way doesn't. You know, in physics, it doesn't have to be rigorous. It only has to be correct. But physicists love Lagrangians. So let's try and incorporate this result here in a Lagrangian so that we can stick our teeth in it. The way to do that is completely standard. The Lagrangian that we start with has a 1 over g squared times s with some pi's and stuff. From this equation, 1 over g squared is like log lambda. So we can think of log lambda as a source for s. In other words, we want a superpotential such that its derivative with respect to log lambda will be this s. So with all the pi's, we would like this s expectation value to be 1 over 3 nc d by d log lambda of some effective superpotential. So it's easy to solve that equation. And derive a formula which is extremely helpful. And again, we see this fractional power here, which tells us that there are NC different vacua. And this NC is such that when you plug it over there, in the derivative formula, this NC cancels that one NC, and the 3 NCs cancel, and we'll land on the coefficient 1. This is an extremely interesting formula, which at first sight looks like it doesn't make any sense. It doesn't make any sense because lambda is a number. And how can a superpotential depend on a number? Because physics depends only on derivatives of the superpotential with respect to fields. So what does this function mean? Before we extract physics from it, we have to say what it means. We can assign meaning to this equation, this superpotential, two different ways. Way number one, weakly couple this theory to supergravity. And in supergravity, the constant in the superpotential makes sense. So that's what this thing is. Alternatively, we can consider not just the Young-Mills theory, but we can take Young-Mills theory with a coupling constant which is space dependent. Very long wavelength, much longer than anything else in the theory. We can make it not only space dependent, we can also make it theta dependent. So we can think of lambda as being a background chiral superfield. And once lambda is a background chiral superfield, this formula makes sense because this is a superfield. In fact, log lambda was introduced as a source. So it should be thought of as a background chiral superfield. So this is what this formula means. What is it good for? It has a number of applications. The first application is that this theory has domain walls.
Log lambda is well defined.
Sorry?
Log lambda is well defined.
Up to phases, which are associated with the shift of the theta angle by 2 pi, which take you from one vacuum to another. So this theory has NC ground states. So we can divide space to half. Say here we are in ground state number 1, and here we are in ground state number 5, say. 2 different ground states. They don't even need to be adjacent to each other. And in between, there is some domain wall. So this is a very complicated structure, but it's a fact about supersymmetric theories that we can exactly determine the tension of these domain walls. And tensions of domain walls are given by the difference of this superpotential between the two sides. So the tension of a domain wall, which interpolates between vacuum K1 and vacuum K2, is NC, lambda to the 3NC, 1 over NC, absolute value, e to the 2 pi I, K1 over NC, minus e to the 2 pi I, K2 over NC. And let me put the absolute value here, because lambda can be complex. So this is an exact result for the tension of domain walls in this theory, which trivially follows once we have this superpotential. Application number 2, once we have a superpotential as a function of the source, if you go to your quantum field theory textbook, they tell you what to do. The first thing you do is a Legendre transform to find the 1pi effective action. So it's straightforward to take this thing. The source is really log lambda. Right? You see we differentiate with respect to log lambda in the last blackboard over there. So we can perform a Legendre transform to find the W effective of S. Which is NC S 1 minus log S over lambda cube. This is known as the Veneziano-Yankelevich superpotential. It's very good for finding the expectation value of S. For example, we can differentiate that with respect to S, set it to 0, find an equation which will give us the same S that we have there. That's what we normally do with Legendre transforms. So we always differentiate with respect to one, we do Legendre transform, get the other. So this is what thermodynamics is all about. But good as it is, it's really important to stress the limitations of this superpotential. S is not a light field. It looks like a glue ball. So it looks like a bound state of two gluons, but it's not. S is a field, but it's not associated with any particular particle in the spectrum. It's a complicated operator in a complicated quantum field theory. If S, the operator S, acts on the vacuum, it does not create a one-particle state, it creates a mess. Correspondingly, this superpotential, or corresponding Lagrangian, is a 1pi effective Lagrangian. It's an effective Lagrangian, but it's not a Wilsonian Lagrangian. It's not a low-energy effective Lagrangian. The reason being that there are no light degrees of freedom in the spectrum. As we said, there is a gap. So this, in order to have a Wilsonian Lagrangian, we need to have separation of scales. We need to have some particles which are heavy and others which are light, and then we describe just the light degrees of freedom. I emphasize that because this is, again, one of these misconceptions. This Lagrangian does not describe any particle. It's certainly not a Wilsonian Lagrangian. Wilsonian Lagrangian is only when we have separation of scale, we have some light fields which we describe, and we integrate out the heavy guys. Here, there are tons of heavy guys. There isn't a single light field, light particle, and there's one operator that we pick out of the trillions of operators that the theory has. And therefore, it's very important to remember that this Lagrangian, as nice as it is, should not be thought of as a low-energy effective Lagrangian for anything. It's not the Lagrangian of any particle. And there are tons of papers which got that wrong. Yeah.
Can it be used for anything except to compute the expectation value of S?
The tension of domain walls. And to write wrong papers. No, I exaggerated a little bit. There could be other applications. But yeah, but it should not be viewed as a global particle that is described by that Lagrangian. But as you will see, I'll extract a lot of mileage out of it. That's why this is where I really deviate from Brian's presentation here last week. I'll take that as a starting point. But I will also emphasize the limitations of that.
Silly question about notation. So lambda was a source for S. So what lambda is doing in function?
Okay, so first to be precise, log lambda is the source of S. And when you do Legendre transform, you see that log lambda here multiplies S. When you call Legendre transform, there are two different things which are called the Legendre transform. You say replace phi with P, and then you either add or do not add the phi times P in the Legendre transform. So here I added it. You would say that the Legendre transform is without the lambda here. Right? You see what I mean? It's when, yeah. The Hamiltonian is minus the Lagrangian plus PQ dot, if you wish. Yeah? So there is still a Q dot that remains. So I like to keep it in so that, the reason I like to keep it in, because you only take derivatives. When you do the Legendre transform, there are two things. You take a derivative, and then you subtract or add something. So I never add or subtract, because I keep it in the effective Lagrangian. Because otherwise I have to remember when there is a plus sign and when there is a minus sign. Yeah, this is just, it's again, it's Professor Legendre already knew all that. So it's not me. Any more questions? So this is what I wanted to say about the flavorless theory. And I guess next time we'll add flavor. This is am my time up or no?
You started 5 minutes late, so you have till 10 to if you want to take
10. Oh, and I have an hour and 15 minutes. Oh, excellent. Excellent. So let's add flavor. Unless there are questions. So we'll add the flavor gradually. With masses m, which are much bigger than lambda. So what happens physically? At very, very high energies, we have some massive quarks. They're very weakly coupled. At energies below m, they effectively decouple. And we have just a pure gauge theory at low energies. And then we can just copy what we did before. So the coupling constant of the theory runs with two different beta functions depending on the energy. And energy is above m, it runs with a beta function of the theory with flavors. And at energies below m, we have the beta function of the theory without flavor. So in order to use the previous results, we have to relate the two different scales. So if the theory had a scale lambda, the analog of this lambda to the 3nc is lambda to the 3nc minus the number of flavors. Flavors always act with the opposite sign to color. So the log of that is the running coupling constant. So this is how things scale above m. Once we pass m, this is the matching relation. Is this clear what I'm doing, or am I talking to myself? Maybe I should explain it again. As a function of energy, imagine we don't have the masses. So the theory goes like that, and the coupling becomes large at the scale lambda. But that's not what we have. At some point m here, the quarks decouple because they are heavy. So above that, the running coupling, so this is g squared. So above energy m, of order m, we use the full beta function. and the coupling constant runs like that. At the scale of order m, the beta function changes, and the lambda that we will get will be smaller. Smaller or larger? It will be larger, because the beta function is stronger. So this is the scale lambda low. And if you just use the beta function, I think I got it backwards. I apologize about that. I'll check it again. I'll use green. At high energies, we go like that. And as m goes to 0, they should go to 0. And then it runs like that and becomes strong at the scale lambda low. Oh, sorry about that. It is larger. We can see it from here, because as we make m bigger, this thing is becoming bigger. Again, I'm sorry. So this is lambda, and at the scale m, it decouples and becomes larger. So at high energies, we have a theory characterized by the scale lambda. Above the scale m, the coupling constant changes. Everything here is still weakly coupled, so we can easily couple it. And at the scale lambda low, the coupling constant becomes very large. And the theory at energies below m is exactly the same as we had before, except that instead of lambda, we should substitute lambda L. So below m, we have an SUNC gauge theory with scale lambda L. So we know the effective superpotential. So now we can express that in terms of the full theory. So without doing much work, we have learned quite a lot about the full theory. And once we have this expression in terms of the sources, little m and log lambda, little m and lambda are like sources, we can differentiate with respect to the source and find expectation values. We can find expectation values, we can do Legendre transform, and so forth. So let me do that quickly. The first thing we can compute is the expectation value of m. This is the derivative of w with respect to m. M is a matrix, of course. So I wrote a formula for this. And the expectation value of S is the derivative with respect to log lambda, just as there. It's dead m. And again, we see the NC fractional powers telling us that the theory has NC ground state. That's not surprising. The low energy theory is just the SUN gauge theory with the same fractional powers, the same NC vacua that we had before. Nowhere here did I make any distinction between the number of flavors being bigger than the number of colors or smaller than the number of colors. This derivation is independent of that. But we see here something surprising, because I emphasized that when the number of flavors is bigger than the number of colors, the rank of the matrix M was constrained to be less than NC. That's not true for the expectation value. This has the full rank. How did this happen? We've discussed before that M is a product of rectangular matrices. Its rank is constrained. And now we just computed its expectation value, and it has a rank which is inconsistent with being a product of matrices. Well, M is a composite operator. It's complicated. It's not just given by two rectangular matrices multiplied each other. It's an object in the quantum theory, and its expectation value does not have to satisfy this classical constraint. This is something we'll see again and again, and here we got it very quickly. This classical constraint that the rank of the matrix M is constrained is not true in the quantum theory. However, if we take M to 0, we can ask what happens to this object. And depending on how many flavors and colors we have, we can get 0 or infinity, or depending on how we take the ratio, we can get different answers. For more flavors than colors, if all the masses are the same, then the 0 here is stronger than the infinity from here. And if we take all the masses to 0, we land on the moduli space, as we should.
Seems that you assumed m much larger than lambda, though, in deriving the formula. Are there corrections of order?
Excellent question. I think you know the answer to this. But thank you for asking.
Why?
In all these analysis, I assume that m is much bigger than lambda. But next time I'll argue that, in fact, this is exact. I tried to pull a fast one, but there are knowledgeable people here. I think I'll stop here. Ask for more questions.
Any questions?
Please. Yeah.
The formula, you pull that out of a hat over here.
Which one?
With the det M.
Oh, this is a one-loop computation.
Right.
So you usually...
To what extent is it determined by dimensional analysis, symmetries, or whatever?
It is determined by dimensional analysis and symmetries, but pragmatically or physically it comes from the one-loop computation. So there is a threshold. The threshold is at the scale m. The way it's usually written is with the log of that. The 1 over g squared is the log of this equation. So the one-loop beta function is 3nc minus nf above the threshold and 3nc below the threshold. And there's a log of that m as you cross the threshold, which is really this plot that I apologize that I first messed up.
Any more questions?
Just going back to what you were saying about the necessity of us living in a metastable vacuum, does that mean that in theory, sort of outside the Hubble radius or something, that there could be parts of the universe that have sort of settled into the SUSY vacuum rather than metastable?
It could be. But we're asking a phenomenological question, and for that we need to have a more detailed model. In the last lecture, I'll present a model, a dynamical model, where we end up in a metastable state. And at least one member of the audience proved that in that particular model, the cosmological evolution prefers the metastable state. And I think he'll give a talk about that on Thursday. Where is he? Here. So this is a little bit outside the scope. Here I'm just doing kind of enumerating what kind of vacua there can be, which might or might not. You're not taking into account finite temperature and the evolution of the universe and so forth.
Okay, let's thank Natty again and go to